Dear students, welcome to Kinematics of Machinery course. In this video lecture, we will learn about kinematic link, properties of kinematic link, types of constrained motion, pair, kinematic pair, and types of kinematic pairs. So let's begin the discussion with link or a kinematic link. According to the definition, every part of a machine which moves relative to some other part is called as a machine. Now, three different practical examples of machines are shown on the screen. The first one is internal combustion engine. The second one is lathe machine. And the third one is JCB, which is an earth moving equipment. Now, all these machines are having different parts. In case of internal combustion engine, it is consisting of piston, connecting rod, crankshaft and cylinder. So say for example, if I consider piston, then the piston is moving relative to the connecting rod or the cylinder. So both cylinder, connecting rod or piston becomes the link. Similarly, if I consider lathe machine, then it is consisting of tailstock, carriage and the cross slide. It is consisting of headstock and chuck, or you can even think of this bed. And all these parts are basically moving with respect to each other. So these parts are having relative motion between them, and hence these parts will be called as link. The same logic is applicable to the third practical example, which is JCB. In this case, this part is typically called as the arm of a JCB, and this part is typically called as the bucket. Now both arm and bucket are moving relative to each other. So these two parts are typically called as link. So overall, every part of a machine which moves relative to some other part is typically called as a link. Now let us discuss about properties of kinematic link. There are two properties of kinematic link. The first one, kinematic link must have a relative motion with any other link. Now, like I said already, the piston is moving with respect to cylinder and the connecting rod. So, cylinder, piston and connecting rod are having relative motion between them. So, even though cylinder is stationary and piston is moving with respect to cylinder, piston and connecting rod all becomes the link or a kinematic link. Now here we need to understand one concept. If you look at this part which is shown in green color, now this part is typically called as a crankshaft, and on this side this part is typically called as flywheel. Now both are basically keyed to each other. So as the crankshaft turn, together with crankshaft, flywheel also has to turn. Means relative motion between crankshaft and flywheel is not possible. So even though these are two different parts for an internal combustion engine, in kinematics of machineries, we will not be calling them as two separate links. Both crankshaft and flywheel becomes one and the same link. The same discussion is applicable for this practical example as well, which is a ceiling fan. Now right at the center you have a rotor, and this is typically called as a fan blade. Now once you switch on the fan, together with rotor, the fan blade also has to turn. Means relative motion between fan blade and rotor doesn't exist. So even though these two are two different parts, in kinematics of machineries, these two parts will be reckoned as one and the same link. The second property of kinematic link is it must be a resistant body. Now we need to understand the difference between a rigid body and resistant body first. A rigid body is the one which does not deform at all while transmitting motion or forces. However, Resistant body is the one which deform while transmitting motion or forces, but their deformation doesn't affect the force or motion being transmitted. Now, as we all know, perfectly rigid body doesn't exist in actual practice. So, a link, to be a kinematic link, it should be a resistant body. Now, with this discussion, let us move ahead and let's try to discuss about types of kinematic link. Now, there are three different types of kinematic links. The first one is rigid link, the second one is flexible link, and the third one is fluid link. Now, once again, three different practical examples are shown right over here on the screen. The first one is, let us say, gears. This one is the chain drive, and the third one is once again the same practical example, which is JCB, an earth moving equipment. Now, rigid link is the one which does not deform at all while transmitting motion or forces. Say for example, these gears. When these gears turn and they transfer motion or forces, their deformation is negligible. We can't see that deformation. So, these gears become the best practical example as far as rigid link is concerned. The flexible link is the one which deforms while transmitting motion or forces, but their deformation doesn't affect the motion or forces that we are trying to transmit. Say for example, the chain drive. Now, chain drives are known to be the flexible drives. While transmitting motion or forces, this chain flex a bit, but their flexing doesn't affect the motion or forces being transmitted. Similar example to this one, you can even think of a belt drive. You can even think of a belt drive which once again flexes while transmitting motion or forces, but that doesn't affect the motion or forces which is being transmitted. So, chain drive or belt drive becomes best example of flexible link. The third one is fluid link. Fluid link is basically formed by having fluid in a receptacle. Now, look at this part of JCB. This is basically the arm of a JCB. We already had a discussion regarding that. On this side you will find there is a bucket, and right over here you will notice a hydraulic cylinder and piston arrangement is shown. Now, in this case, the pressurized fluid will be pushing the piston in and out, and that motion will be used or transferred to the bucket to do different earth moving operations. Now, in this case, the motion between two links is obtained through the pressurized fluid, and hence this type of link is typically called as a fluid link. Now, with this discussion, let us move on and try to understand what do you exactly mean by pair. When two links comes together, they are said to form a pair. Once again, please pay attention to the same practical example. What you see right over here is the arm of a JCB, and what you see right over here is basically the bucket. Now, both of them are basically part of a machine, right? And both are pinned to each other at this particular point. Now, since the bucket and the arm are moving relative to each other, they becomes kinematic link, and both are pinned to each other at this particular point. So, they form a pair over here. So, when two links comes together, they are said to form a pair. Now, before moving to types of kinematic pair, let us try to understand the types of constrained motion. Now, there are three different types of constrained motion. The first one is completely constrained motion, the second one is incompletely constrained motion, and the third one is successfully constrained motion. Now, to understand this one, let us have a look at figure number 1. Now, in this figure, I have considered two links. Let me call this as link number 1. Let me call this as link number 2. Both are coming together to form a pair, obviously, and let's try to understand the motion between these two pairs. So, what I'll do, I'll try to push this link number 2 in this direction. The output motion can be seen in this direction. If I try to pull it something like this, then the similar type of output motion can be seen. Even if I try to apply incline forces to link number 2 like this one, I'll notice the similar type of a output motion, and if I try to twist it, it will not allow that twisting. What do you understand with this practical example is motion between link forming a pair is limited to definite direction. So it can take place only in one direction irrespective of direction in which force is applied. I am trying to apply forces in different directions, but it is giving you only one motion. In this situation, this type of motion is typically called as a completely constrained motion. Now let us go and understand incompletely constrained motion, the second type of a constrained motion. Once again, I have considered two links. Let me call this as link number 1 and link number 2. Now in this case, it is basically a square block which is having a circular hole and a circular shaft is passing through. In this case, I'll do the same thing. I'll try to apply a force in this direction. It will show me this kind of a motion. If I try to pull it in this direction, it will obviously come out. Even if I try to turn it in this direction, it will try to turn. So output motion between two links forming a pair is not definite, not occurring in a definite direction. It is basically depending upon the direction in which force is applied. And in this particular situation, this type of motion is typically called as incompletely constrained motion. Let us understand the third practical example, which is successfully constrained motion. Now figure number 2 and figure number 3. Let me call this as figure number 3. Both are one and the same, but there is only one difference, and the difference is right over here. What you see right over here, this is typically called as a collar. So let me call this as link number 1. Let me call this as link number 2 again. Now if I try to push it in this direction, well, no output motion is possible. That is because of collar, obviously, right? If I try to pull it in this particular direction, still output motion is not possible. However, it will only allow turning in clockwise or anti-clockwise direction. Now this basically goes into the category of completely constrained motion. But if I remove this collar, then it becomes a incompletely constrained motion. Why? Because in absence of collar, you can push it, pull it out, you can turn it in clockwise or anti-clockwise direction. So depending upon the direction in which force is applied, the output motion will change. So it is the collar which is bringing that completely constrained motion in this pair, right? So the third member is responsible for constrained motion, and the constrained motion is not obtained by the pairs which are forming the pair. Link which are forming the pair. So this type of motion is typically called as a successfully constrained motion. Now let us go and understand the different practical examples. Now the first practical example is a tire which is rolling around the axle. Well, this is obviously the tire can only turn in clockwise and anti-clockwise direction, right? So this becomes the best example of a completely constrained motion. The second practical example is a lathe machine, especially this tailstock, which can only slide with respect to the bed. So it becomes a practical example of a completely constrained motion. If I think of this drill machine and then the chuck of a drill machine, then it can only move in up and down direction. So it becomes a completely constrained motion. But if I think of this table, right, this table can swivel like this one, and even it can move in up and downward direction. So that becomes practical example of an incompletely constrained motion. If I think of this arm of a JCB, example number 4, so once again this bucket can only turn about the arm of a JCB. So it becomes a completely constrained motion. This is basically a footstep bearing, and in this footstep bearing, this shaft can turn in clockwise or anti-clockwise direction. But if I try to pull it out, or if I try to take it out, because of this thrust load which is acting right at the top, it cannot be pulled out, right? So once again, same situation. If this thrust load is not present, then it is possible for me to take it out and turn as well. So that becomes a incompletely constrained motion, and in case of thrust load, this becomes the completely constrained motion. So this is basically best example of a successfully constrained motion. Number 6 is nut and screw. So obviously in this particular case, motion between two links is limited to definite direction. This nut can only advance with respect to the bolt, so this becomes best example of a completely constrained motion. Number 7 is incompletely constrained motion, because I know I can turn this one in clockwise or anti-clockwise direction. Similarly, I can slide it on, right? So this becomes the best example of a incompletely constrained motion. Instead of having a circular rod over here, if I use a square rod, square section rod in this practical example, then the twisting will be automatically restricted. It will only allow it to slide. In that particular case, this becomes a completely constrained motion. Number 8 is mirror of a bike. Now this mirror can turn in absolutely any direction depending upon your requirement. So this becomes the best example of a incompletely constrained motion. And number 9 is obviously piston, which is sliding with respect to the cylinder. So it can only slide in one direction. So once again, this becomes the best example of a completely constrained motion. Now let's try to understand what do we exactly mean by kinematic pair is. Now we already know that when two links comes together, they are said to form a pair. However, if the pair is transmitting completely or successfully constrained motion, then that pair can be called as a kinematic pair. So when two links are coming together, well, a pair is formed, and if that pair is transmitting completely or successfully constrained motion, then that pair is typically called as a kinematic pair. Say for example, let us try to understand this particular pair which is formed between tailstock and a bed. Now in this particular case, the tailstock can only slide with respect to bed. No other motion is possible. So this pair is transmitting a completely constrained motion, and hence this pair will be called as a kinematic pair. So if a given pair is transmitting completely or successfully constrained motion, then that pair will be called as a kinematic pair. Now let us try to understand types of kinematic pairs. There are three different types of kinematic pairs. There are three, the kinematic pairs can be classified based on three categories. The first categorization is based on type of relative motion between the link. The second one is based on type of contact between the link, and the third one is based on type of closure. So let's go and understand each of them one by one. So the first classification is based on type of relative motion between the links, and the first pair is a sliding pair. Now when two links comes together, they are said to form a pair, and the pair is formed in such a way that one can only slide with respect to each other. One can only slide with respect to the other link. In that particular case, the pair formed is called as a sliding pair. Now if you think of this example, in this particular case, let me call this as link number 1, let me call this as link number 2. The link number 2 can only slide with respect to link number 1. So only sliding motion is possible between these two links. So this type of a pair is called as a sliding pair. The second example is this one, piston and cylinder arrangement in case of internal combustion engine. Once again same, this piston can only slide with respect to the cylinder. And one more practical example is right over here, the one which is already discussed, tailstock of a lathe machine. So this tailstock can only slide with respect to the bed. So sliding pair is the one in which one link can only slide with respect to the other one. Another name given to this pair is prismatic pair, means sliding pair is also called as a prismatic pair. Now if you look closely, sliding pair transmits obviously completely constrained motion. Let's move on to the next one. So the next type of pair is turning pair. Now when two links forming a pair are connected in such a way that one can only turn with respect to the other one. One can only turn with respect to the other one. Let us understand the concept with this figure. Once again, let me call this as link number 1, link number 2, and if I notice, this link number 2 can only turn with respect to link number 1. So this is typically called as the turning pair. Now one more practical example to this one is the axle of a bicycle or a bike right over here. Right? So this bike wheel turns with respect to the axle. Only turning motion is possible. Even you can think of this practical example, which is JCB, where different arms are pinned to each other. This particular arm is pinned to this arm. Even this arm and the bucket are pinned to each other at this particular point. So basically between the arm and the bucket only turning movement is possible. So this pair is typically called as a turning pair. Another name given to this one, this pair is also called as a revolute pair. The third type of pair is a rolling pair. When two links comes together, they are said to form a pair, and if one is connected in such a way that it can only roll with respect to the other one. So when two links forming a pair are connected in such a way that one can only roll with respect to the other one, then the pair formed is typically called as a rolling pair. The best example is obviously the ball bearing. Now what you see right over here, this is typically called as outer race of a ball bearing. This part is called as inner race of a ball bearing, and between inner and outer race you will find the steel balls are rolling over inner and outer race, right? So between ball and inner and outer race only rolling is possible. So this becomes best example of a rolling pair. Another practical example is a wheel which is rolling onto the road surface. So if you look at these wheels tend to only roll over the road surface. So this becomes the best example of a rolling pair. Moving on, the next type of pair is screw pair. So when two links forming a pair are connected in such a way that one can turn as well as slide with respect to the other one. Say for example, this is nut and bolt arrangement. Now if I'll be turning this particular nut in clockwise or anti-clockwise direction, together with turning, it will also give you a sliding motion. So sliding and turning motion are occurring side by side, and this type of a pair is then called as a screw pair. The best example is right over here. This is called as a screw jack, which is typically used for lifting of automobiles. So if I'll be turning this one, right, together with turning, it will give me a sliding motion as well. The same logic is applicable right over here, which is a lead screw of a lathe machine. Screw pairs are also called as helical pair. So that is the another name given to the screw pair. The next one and the last one is spherical pair. So when two links forming a pair are connected in such a way that one element which is in spherical shape can swivel above the other one. So look at this one. You will find this element is basically in a spherical shape and it is swiveling with respect to the other one. Practical example for this one is obviously the pen stand. If you pay attention to this point, you will notice the end of the pen stand is having a spherical shape, and this pen holder can swivel above that particular stand in any direction. This is another practical example, which is mirror of a bike, right? and depending upon your requirement, there is a spherical pair right over here. You can adjust the mirror in any direction. Spherical pair is also called as a globular pair. There is another name given to it. So this is the first classification. The second classification is based on type of contact between the links. So you will have a lower pair or you will have a higher pair. When two links forming a pair have a surface contact, then the pair formed is called as a lower pair, and if you are having a point or a line contact, then the pair formed is called as a higher pair. Now there are number of examples shown right over here. This is the first one, piston and cylinder. If you notice, between piston and cylinder there is a surface contact, so it is basically a lower pair. If you look at the second practical example, which is bike running onto the road surface, right, you will notice at this there is a point or a line contact, so this becomes a higher pair. This is screw jack, which is between nut and bolt there is a surface contact, so this is best example of a lower pair. This is once again same paint stand, it is giving you a surface contact, so this is basically a best example of a lower pair. And the fifth and the last one is gears. Right at this point you are having a point or line contact, so gears becomes best example of a higher pair. Now we already had a discussion regarding this one. This pair is typically called as obviously sliding pair. This pair is typically called as a rolling pair. This pair is typically called as a screw pair. This pair is typically called as the spherical pair, and this pair is typically called as a rolling pair again. So sliding pairs are lower pair, rolling pairs are basically higher pair, screw pairs are basically lower pair, and spherical pairs are basically lower pairs again. So let's try and understand the last classification, which is based on type of a closure. And the first category in this one is self-closed pair, and the second one is force closed pair. In case of self-closed pair, the constrained motion is obtained by link which is forming a pair itself. Say for example, if I think of gears, then in gears the constrained motion is formed by the gears which are forming a pair itself. So in that particular case, that type of pair is typically called as a self-closed pair. The same discussion is applicable to even this particular screw jack. The motion between two links can only take place in one direction, right? So the constrained motion is obtained by the link forming pair itself. Right, so these types of pairs are typically called as self-closed pair. The second one is force-closed pair. In case of force-closed pair, the constrained motion is obtained by external forces. As you can see in this particular case, which is in which this thrust load is responsible to create the constrained motion between the shaft and the bearing. Even in this particular case, which is cam and follower type of arrangement, to bring cam and follower in permanent contact with each other, you are using a spring force right over here. So the constrained motion is basically obtained by external members. In this particular configuration, the pair is typically called as a force closed pair.